Hello, this is part two of the first lecture or lecture PowerPoint slide deck on the Introduction to Intelligent Systems E500 course describing my work in my and others' work in cyber infrastructure, clouds, HPC, and a little bit of physics, but I gave you the physics in part one, so there's no more physics in parts two or above. So here we go. Yes. So you can tell history. I was telling you the history of what was going on in 1967 when computers were just being introduced, and I was fascinated by them. Here is what happened in 2011. I went to a American Indian College in Pueblo, Montana, and we gave them a cyber infrastructure day. We told them all about cyber infrastructure. And I use this talk just because I actually haven't given a general talk on cyber infrastructure since then. I have been doing other things like trying to run this department, and it is an interesting snapshot of what we thought at the beginning of the big data revolution. Now big data is so common that actually we would do it differently, but maybe this approach has its advantages. So, all right. So this is what I used to start with, the trends of 2011, which may or may not be. They are related to the trends now. Data deluge. Don't think we use that term quite as much as we used to. The deluge of data is another way of saying big data. The multi-core effect, namely that all computers have lots of cores, and we're getting performance not from the extra clock speed as we used to, but from the extra cores. This has now been going on since 2008, and so it's built into everybody. GPUs are now even better known than they used to be, and the fact that they can give a power boost was true then and true now. Clouds are now more important than they used to be, and actually they've changed. Clouds are now everything. Previously, they were just what commercial people did for the initial commercial big data problems. And as I say here, they sort of replaced computer grids. Nobody ever said that, but it just happened. And if you look, you'll see the word grid disappears almost synonymously with clouds appearing. And actually, nowadays, they will replace your general purpose computer center, such as the one just next to Smith Research Center. Well, here's a reasonably insightful remark. Lightweight clients. The Internet of Things. Well, we have even more emphasis on that now than we used to. It's becoming of age, and it's really obvious that it's important. But even in those days, sensors, smartphones, tablets with cloud backends were perceived to be a wonderful trend. And the same is true here. It's true now. The commercial efforts are moving much faster than academia. The commercial companies are introducing the revolutions in deep learning and large-scale data centers and so on. All right, so these trends were true then, they're still true now. They have somewhat different impact now, but there's nothing wrong with these trends. All right, here is a chart from one of my students who graduated a year or so before then, and it's sort of out of date. This uses big data and takes estimates we wouldn't use today. And I should point out that actually, if you look at my surveys, no longer do we plot the amount of data created per year. It's now so obvious, it's just enormous. People like Mary Meeker, who has this nice internet trends discussion each year, doesn't give the same details on data that she used to. Notice that the data in these days was 1,200 exabytes to 2010. Nowadays, I think it's 6,000 to 8,000 exabytes. These are those which is 6 to 8 zettabytes. Zetta. All right. Notice the difference in enterprise storage and total storage. This is of course an old statistic: 220 petabytes per day in 2008. It must be much larger now for Google. Web page size, I don't know how much that's increased. It's certainly increased, but there is some attempt to reduce. I mean, web pages are only useful if they're looked at, and there is increase in number of people looking. So it's not going to rise maybe quite as much as the amount of data. Drones are producing huge amounts of data. That's a drone is a very important thing in the Internet of Things. And that amount of data is going to dramatically increase. And this corresponds to the fact that sensors, such as those in cameras, are getting more and more powerful. For the same reason, computers are getting more and more powerful. Moore's law. You can get more bang for your buck in a certain area of silicon. Here is statistics about genomics, which is certainly dramatically out of date. Walmart is being suddenly doing its thing to try. I mean, it must be much larger because it's competing with Amazon, and Amazon is driving huge innovation in e-commerce. Then we have lots of tweets every day. Well, I don't know what that number is now, but it's more than 90 million, I'm sure, although for some reason, Twitter's use is not dramatically increasing. Instagram and Snapchat WeChat increase faster than Twitter. Then we have lots of science data, astronomy, particle physics, medical records. And then we have the fact that this implies the need for lots of I/O to read the data, although that does critically dependent on the amount of data analytics you do. If you run a very sophisticated algorithm, that I/O doesn't matter. The only reason the I/O is important if you do almost no processing. Then there's the so-called fourth paradigm, data-intensive scientific discovery, and we have the 100 petabytes used to find the Higgs boson. The fourth paradigm of science, which is after the third paradigm, computational science, second paradigm, experiment, first paradigm, theory. That fourth paradigm is where in the classic approach, you use theory to interpret experiment. In the fourth paradigm, you use data to interpret data, or data to interpret experiment. But that data, of course, is the result of the experiment. All right, this is this multi-core effect. Here it sits in 2008, but it's been going on since then. Frequency is leveled off, and in fact, you often run it lower than this frequency for power reasons. And that is simply due to the amount of power needed goes up too fast if you increase the frequency. So now you used to be actually get good performance in three reasons. You increase the clock speed because you had smaller devices, therefore things ran faster. But you also got more devices per square centimeter, and so that also did increase performance. So, and now we're doing multi-core, which means in a given chip you have lots of cores, like the nice landing chip we have has 68 to 72 cores on every chip. And we're getting additional performance because we have those 78 cores running simultaneously on a single chip. Whereas previously, we just ran our chip faster and it ran just one core. So you just, but you've gone from some sort of cubic dependence on size or inverse size to a square dependence because it's just the area effect, not an area times clock speed. Here is, well, this actually, I can update this slide. It's just on the web, and it's the cost per genome, and it shows Moore's law, and you can see that the cost is, this is an illustration of why big data is so prevalent. The instrument driving genomics has got faster, much more fast than computers have. So computers are sort of been revolutionizing the world for a long time. But now instruments are sort of doing it even faster. And that is one of the reasons why big data is so exciting and so important, and also why the whole sort of computing aspects of big data has changed, because our computer power is not keeping up with our data. All right, now we come to some slides about what is cyberinfrastructure. And it is the infrastructure that supports, by definition, distributed research and learning Other names for it or related names are e-science, e-research, and e-education. Those are the applications to science, to research, and education. And cyber infrastructure links data, people, computers. And those computers do data analysis and simulations. Cyber infrastructure uses Web 2.0, which was common in 2011. You don't see it as often today. It uses clouds. Then it uses grids to link everything together. At least in science, all the data is distributed because all the people are distributed, but there's only one science. You only have one law of nature, and that is studied by everybody around the world. So you have a distributed system studying science. I've already stressed the difference between parallel computing and distributed computing with low latency and highest latency, microseconds to milliseconds. Where parallel is needed to get high performance on individual problems. Build a new battery. Understand the one and only universe. And also maybe do some high precision clustering or something like that. There you take the problem and you shard it. You break it up into parts. Distributed integrates already distinct components, such as all the different things of the environmental sensors gathering data around the world. All right, so we generalize e-science, etc., into E, more or less anything. You can put E in front of everything, and there's probably a startup for anything there is. When I was at the Consumer Electronics show in Las Vegas in January, there were startups for everything from looking after your pet, controlling your audio, controlling your car, your vacuum cleaner, your lawnmower, what have you. Lawn mowing, pretty important, is it not? So John Taylor, who was from Hewlett-Packard, but then became so-called Director General of Research Councils, probably similar to the head of NSF or maybe even higher than that. And he invented e-science, and the United Kingdom was a pioneer in e-science, led by one of my friends, Tony Hay. And e-science is the research equivalent of e-business, where e-business or e-commerce is really common today, because it's what's driving the disappearing shopping malls, because everybody is doing things online. Intrinsic to e-science is virtual organizations. I told you I was ahead of the time with InfoMail. That was a virtual organization in 1995 or 96, I forget exactly which year. Well, I tried to do it for actually 5 years, but it started around 95. And virtual entities are intrinsic to the internet, because the internet does link everything that's distributed and try to make it a single whole. And then we have e-digital library, e-fine arts, e-having fun, or e-social media is obviously a dominant trend today. E-education is sort of online education and Coursera and MOOCs and things like that. We have the deluge of data, which we have to understand. And we must link people, computers, data, and networks are all involved in E more or less anything, illustrated by e-science for the research endeavor in science and, of course, engineering. All right. So this cyber infrastructure links the conferencing technologies. Zoom is what we use today. In those days, we used so-called Access Grid, then Adobe Connect, all sorts of WebEx, sorts of technologies. Digital libraries with music, curricula, scientific papers. All these things. Flickr is no longer as important. YouTube and Amazon are improving / hanging in. Simulating a new battery design. That is the large single problem that you might use on your exascale supercomputer. The virtual observatory shares the data from all the telescopes, and if you look at those telescopes, they operate at different wavelengths. We'll see that later on in this presentation. And then the virtual observatory allows you to compare data at different wavelengths. You then use the cloud. You analyze your personal genome from, which you can get now commercially. I bought my personal genome for $99 on Amazon at their last sale. All right, then we all need to this is citizen science or crowdsourcing. We want to be partners together online to create knowledge and convert it to wisdom. Remember, we do data, information, knowledge, wisdom, decisions. And then we can, of course, more recently, lots of people have shown how you can analyze tweets to try to understand everything from earthquakes to stock markets to disease and things like that. Possibly even the ranking of institutions. All right, here is multi-wavelength astronomy. And we have these different here's the old one. I was at Caltech when, actually after the Palomar telescope was developed. It is just a little south of Caltech in Pasadena. And it is, of course, a premier optical telescope. I think it's 200 inches. But now you have lots of other telescopes, those on satellites, and those which are analyzing the different wavelengths, such as the square kilometer array is a radio telescope, which is very, very powerful, and which is going to have huge amounts of data sometime around 2022. This comes from a friend of mine, Fran Berman, who at the time was at the San Diego Supercomputer Center. Here is another thing about Virtual Observatory. It shows the same region of sky in 6 different wavelengths, showing how it's pretty different. Here is the classic beautiful pictures of galaxies. It's probably an elliptic, edge-on spiral, a front-end spiral, and showing radio, infrared, X-ray, and so on. It looks pretty different in different wavelengths, and each tell you something. Here is something which is now rather old-fashioned. These are sequencing devices. Illumina is still actually the dominant vendor in the field. They buy up all the other companies. Those give you the reads, which are sort of, they vary in size, hundreds of possibly characters per read. You align them, and then you produce your sequences, genomes. Then you can actually try to understand the different genomes by clustering them, calculating the difference between them, seeing what genomes are similar to what others. And when we do that, we get a mixture of MPI, low latency data analytics. We do visualization. And we also do large-scale, pleasingly parallel computations to find the different distances. And all of this data comes from the internet, lands somewhere, runs through this data analysis on demand. It uses MapReduce or enhanced MapReduce with a system we have called HARP. And that is classic big data. Here is a typical result of visualizing the result of some sequences of 100,000 metagenomic sequences, and you can see very clearly that when you project this to, well, it's 2 dimensions, but it was originally 3 after the projection, but I rotated it around. You can see very clear clusters showing that there are a lot of different families here, and that they are actually identifiable. Here is another project we have with Kansas. This is looking at data gathering. We have the so-called Polar Grid Laboratory, which we had at both Indiana University and Elizabeth City. That's now finished, as this project is sort of winding up, because this started in 2008. In fact, it's 2007 was the award. So that's a finished project, because it probably lasted 3 years and 1-year extension, so it ended around 2011. And it's sort of interesting, the data from the north and south poles, which you need to study glaciers. There is not enough bandwidth to transmit it back to Indiana University to do the analysis, so you have to write the disk and ship the disks. And then you take your data by flying planes or driving cars or dragging things around. Here's what you're dragging around your sensor. And here's students at Elizabeth City State in Elizabeth City, North Carolina, analyzing that data. So that's the Polar Grid project. All right, here's some general stuff about data centers. Clouds are basically a data center technology. They have explained how to build much larger data centers than anybody's ever had before. And they've been able to do it at a cost that's much cheaper than before by very careful optimization of power and cooling and things like that. and running the systems in a highly fashion which is not just optimized for performance, but optimized for power, overall cost performance, where that cost is not just a piece of hardware, but also the cost of the power needed to run it, and the power needed to run the cooling and everything. And here we see a ratio of about 7 to 6 in the various components of a data center between a small side, 1,000 servers, which is actually pretty big by some people, it's big by our standards, and a larger 50,000 server center. Notice you need fewer people per server to run the larger center, and probably you'll get better people because you can afford, if you're actually there doing servicing more computers. And remember, that's only possible because these computers are all identical. Well, not all of them, but a lot of them are identical, so you can use the same management techniques. You can pick and choose the people and get people which are probably in general have a higher skill level. And here, the size of these data center, the order of magnitude more than a football field. Here's the football field. If we look in a little more detail about Google at the Columbia River, they each have they'll be running soon 50 megawatts per center because there's around 150 watts per CPU, and they save money by using hydroelectric power or whatever power is cheapest or wherever they get the best deal. And they need, of course, good access to the internet because the people are going to be accessing these systems from the internet. Here's another slide where we're using this sort of rackable technology where people trucks just drive up a shipping container, and that shipping container is just full of, each container has 200 to 1,000 servers, and you just build it around the shipping container. So that makes it very easy to upgrade and things like that. You just have a factory building shipping containers for the computers, and then you just drive up those computers, plug them in, and you're ready to go. Pretty interesting. There were once experiments on how you would actually, you could stick these computers in the snow because then they'll be automatically cooled and things like that. It was all due to these studies on how to do not the highest performance computer, which is what I used to study, but the most cost-effective computer where you put everything at the cost, the people, the CPU, the cooling, the repairing, and everything. Not so trivial how to do that. All right, so now we come on to a little discussion of the different types of systems we have. And here I'm going to discuss grids, MPI, and clouds. So grids, which in 2011 was still pretty popular, no longer really very popular, they are distributed systems by definition. And those started in around 2000, whereas clouds were 2008. And classic supercomputers have been going forever. 1980, maybe. Let's call it 1980. All right. So the grids pioneered a lot of the key ideas like services, like the importance of workflow orchestration. And they have this performance issue I've stressed, that tens of milliseconds between the different components of a grid in latency. And therefore, they cannot be used for parallel computing. They can only be used for distributed computing. Clouds have lower latency than grids because they are typically run on clusters, large clusters. I told you, 50,000 servers maybe. And they have these nifty things like you only pay for what you use. You can expand up your use when you need it, so-called on-demand. MapReduce is the favorite technology, which is somewhat easier to use than MPI, but has much lower performance. Originally developed for things like databases that do not require high performance. And the original clouds were not terribly optimized for MPI, and the locality of the computations, which are well understood. You need to keep your computing near the data. But those are those are improved. And in fact, you can see here, I noted in 2010, Amazon announced an HPC cluster. So now we're 2017. They have lots of HPC clusters you can rent. But probably the most sophisticated parallel high-performance systems will run on supercomputers, which are optimized for MPI. And they're optimized for very large jobs. And they do simulations and not data analysis, although people will try to make them do data analysis because that's needed. And those are, if you like, your favorite MPI engine. And we noticed that MapReduce does more work than MPI because MapReduce is dominant in industry, and industry is bigger than science. All right, now some comments on jobs. All right, these are a little old because these are predicting jobs in 2015. Some of them are, like 2.4 million new computing jobs by 2015. I have no idea whether that prediction was correct. These IDs are well-known companies. Gartner, IDC are well-known companies for making such predictions. And this is why clouds are so popular with graduate students, so many industry jobs, because every company in the world needs to use a cloud. All projects focusing on workforce development would naturally involve clouds. Here is a famous thing called a hype curve, and this is from pretty early, hype curve in 2009, with cloud computing at the top of the hype curve. This is the peak of inflated expectations. So clouds were introduced in 2008. They rushed up this technology trigger, got here, and then now they've actually left the hype curve because they're so well established, they no longer need to be put on this curve. And big data is not yet on this curve. It will occur very soon after 2009. Here is 2010. Cloud computing has gone up on cloud web platforms. Similar concept sitting here. This is 2010. Unfortunately, this is an overlay, so you see the things I wrote onto the 2009 one. But otherwise, it's pretty similar. Robots are coming along here. Social analytics, that's obviously very important. Here we have self-driving cars, autonomous vehicles, starting up the technology trigger. And then we have here another graph that these people make called which plots the benefit from low to transformational against time. And we have cloud computing, media, tablets in the 2 to 5 year out, transformational. I think it's fair to say cloud computing is transformational. Things like analytics, they're just putting in high. Analytics is pretty important. 3D printing is transformational. It probably happened in less than 5 years. Here we have self-driving cars. Here is more than 10 years. Mobile robots. These things here still make sense. So augmented reality is still being worked on intensely. Virtual assistants, Alexa, Google Assistant, Cortana, these are all Siri. They're very important. Here we have a 2015 hype curve. And here we have a little bit of cloud computing left. We have augmented reality still here. Enterprise 3D printing, Internet of Things, analytics. That's intelligent systems in the language of ISA. Here we have autonomous vehicles at the peak of inflated expectations. Machine learning, we all want to study. Wearables, we do work in that area. So consumer 3D printing. So these are all things we would like to understand. Here we have 2016, and now there is no cloud computing at all. And we have still machine learning up here. Augmented reality, virtual reality. These are still not taken off. Back here, we must have some nifty things. Quantum computing. Neuromorphic computing. These are specialized hardware to do deep learning and so on. 4D printing, time-dependent printing. All right, we go from 2015 to 2016. They lost 14 technologies. where I circle the ones in red are the big data relevant things, hybrid cloud computing, advanced analytics. It's not that these things are unimportant, they just mean they probably become so obvious they don't want to put them on a hype curve. Internet of Things has taken off in 2016. It's just well established. Digital security is taken off. New technology, blockchain, a very important technology for distributed ledgers. General purpose machine intelligence, well, that's intelligent systems of ISE. Neuromorphic hardware, I've mentioned that before. Connected homes, commercial UAVs, drones, machine learning, ... So these are all the new things coming along in 2016. And these have these four, what you might call, here's the mature cloud, mobile, social information technologies. Charging up the slope of enlightenment, driving change all over the place. Closing down shopping malls. Then we have digital business. The blockchain is the obvious example of digital business. 3D printing is another digital business. It's actually enable you to print on demand things. AI, here we have the big AI revolution. This is a mega trend. And this is all being put into new design and innovation approaches. So this is a pretty interesting way of thinking about what's going on. And finally, we have the 2017 hype curve. And I just wrote it out here because it's easier to read. And I've colored it by these three trends of relevance to ISE, IoT, big data, computing systems, smart dusk, which is just small, very small IoT all over the place. We have these big data things which are all connected with machine learning and specialized hardware for analytics. Brain-computer interface, smart workplace, everything is smart. At the peak, we have edge computing. That's IoT driven by the cloud. Smart robots, IoT. IoT platforms, the software to make this work. Virtual assistants, connected home, deep learning, machine learning, self-driving cars, cognitive computing, Watson, blockchain, commercial UAV drives. These are all the trends of today. And I think it's obvious they're correct.